Okay. Let us wait a couple of minutes. If anyone else wants to join, and then we're going to start.
Can you hear me, Estivali?
Yes.
Okay,
yeah, perfect. Okay. Okay, I think we can start. So, well, good morning, everyone, and welcome to this session dedicated to the BlueFeed Cluster. This is a collaborative alliance bringing together 6 Horizon Europe projects working toward a healthier and more resilient and environmentally responsible aquaculture and a feed sector in Europe.
The cluster unites the projects NeoGiANT, POLYPUFA, SwitchFloc, ActFast, Microbonds for Soy, and auequa.org. While each project addresses different scientific and technological challenges, they all share a common ambition: transforming the future of aquaculture through innovation and sustainability.
Okay. So, well, today we will hear from representatives of these projects who will present their latest developments and explain how their work contributes to this shared vision. So let's begin with Francisco Javier Alarcón, representing NeoGiANT. So he will introduce the project's objectives and the key achievements of the project. So Javier, the floor is all yours.
Okay, thank you. Okay, can you move to the next slide? Well, as we said in the last, good morning, everyone. As we said in the last webinar, we are working with a margrape strat. In this case, we produce a pre-commercial product between the two spin-off working in the project, E-grape and light bio encapsulation. And we produce a functional ingredient consisting in a blend of the margrape strat and microalgae. The product, and you see here, is called green grape. And the product have a typical polyphenol content where we can find the typical polyphenol of grape. The next slide, please. With this, next slide. Okay, with this functional ingredients, we make different pre-commercial feeding trials in different species, and one in sea bream juveniles, another in rainbow trout, and in the first with the amberjack juveniles. All the feeding trials, we elaborate experimental diets for testing growth performance, intestinal microbiota, intestinal functionality, and oxidative status, among other parameters. I will show you some of the ingredients, some of the results that we have obtained in this slide, please. This is the first feeding trial. In this case, you can see the table with the ingredient composition of the experimental aqua feed. In this case, we use a control diet with a normal content of fish meal and a very extreme experimental feed with a very low content of fish meal. We introduce a lot of plant protein. It's a very extreme diet. The other treatment is PPGG, is the extreme diet supplemented with the NeoGiANT product. You can see in the right of the slide the typical profile of the polyphenol that we can find in the PPGG. Okay, next slide. This is the results. And you can see in the number 1, the growth of the fish was reduced with the PP diet because it's a very extreme diet. And you can see in the PPGG that the supplementation with the functional ingredients partially reverse the loss of growth. You can see also in the number 2, the food conversion ratio is increased with the use of the PPG compared with the very extreme diet. From that point of view, the economical point of view, you can see how the inclusion of the functional ingredient can solve some money for the production of the aquafeed. In this case, 61 euros per ton of feed we can solve. Next slide. From a physiological point of view, we tested the digestive enzyme as a tool for knowing how the functional ingredient is working. You can see in number 1, 2, and 3 how the digestive enzyme, this is a typical protease activity, increased with the use of the functional ingredient. In the number 5, you can see also a seismogram of the alkaline intestinal protease, and you can see how there is no changes, it's the same profile in all the cases. Next slide. We test also the antioxidant response. Overall, we evidence that the inclusion of the functional ingredient reduce the generation of reactive oxygen species. So the functional compound confers some antioxidant properties to the fish in the different tissues we tested: the liver, the muscle, and the intestine. Next slide, please. Also, we check the intestinal mucosa as an important tissue for testing the integrity, and we use light microscopy and also electron microscopy for testing and for measuring different parameters. For example, you can see in the 10 images that we measure the length of the microvilli. Next slide. And the results that we obtain numerical results after measuring the slide, the images. And you can see in the number 1 that the use of the functional ingredient increase the fold length, also increase the microvilli length of the enterocyte area of the. So we can affirm that the functional ingredient improves the integrity of the intestinal mucosa in searing, especially in animals supplemented with the functional ingredient. Next slide, please. Also, in this case, we check the microbiota of the intestinal microbiota of the fish. The main finding that we found is that the use of the functional ingredient contribute to restore the microbiota composition compared with the control. You can see in the middle the PP for treatment that changes the profile of the intestinal microbiota, and you can figure that as the PPGG can restore the profile to a similar pattern compared with the control group. Next slide, please. The second feeding trial was performed with trout, rainbow trout. In this case, we use 2 different formats of the product: is the liquid product and the solid product, and different versions of the functional ingredient. You can see in the number 1 the typical profile of the polyphenol compared with the control. Next slide. In this case, we found just a little bit more growth in the animal, in the fish that eat the liquid format, but the rest of the zootechnical parameter was similar in all experimental groups. Next slide. This is a feeding trial performed in a commercial farm, in real commercial situation. In this case, we tested also the intestinal mucosa, and we used the the light microscopy, electron microscopy images to measure different parameters in the intestinal mucosa. And again, we found in the number 1 that as the functional ingredient can increase the total absorption surface in enterocyte. So we can also find here that the intestinal mucosa is improved by the use of the Margrave extract. Next slide. Also, in relation with the last, we tested also the expression of K intestinal gene. In this case, we found that the occludin is a protein that joins the enterocyte. The expression of this gene is increased in the animal that feed the functional ingredient compared with the control diet. So we tested here in other way that the functional ingredient also provided advantage compared with the control, what included in the diet. Next slide, please. In this case, in the liver, we tested also the expression of the antioxidant activity. This is a set of different enzymes. This is the expression of this gene. Also, we find also that upregulation of this hepatic antioxidant gene. So we can say that the functional ingredient provide antioxidant tools or response to the fish. This slide, please. And the third and the last trial is performed with amberjack. It's a very carnivorous species. In this case, we use different dose, different level of the polyphenol. This is the 2 different levels. You can see in the right the graph of the typical polyphenol content, and depending on the dose, we find different level. In this case, next slide. After performing the feeding trial, we do not find any difference in growth. All the fish grow in similar way, and also there is no difference in the muscle chemical composition among the different treatment. Next slide. And again, in this case, we also tested the intermediate metabolic parameters, and we can confirm that the use of the polyphenol can modify the different intermediaries. You can see in number 1, as the medium level increase the triacylglyceride in the plasma, and also you can see the level of the cortisol is reduced by the medium level of polyphenol, and also you can see how cholesterol is modified by the use of this functional ingredient. The rest of parameter was similar in all the liver, plasma, muscle. Next slide. And again, we check it. We analyze the intestinal mucosa in this fish species. In this case, we perform another different test by using electrophysiology. In the right, you can see the graph that we obtain. You can see how the medium level increase the mucosal integrity. This is the electrical circulation around the mucosa, the intestinal mucosa. And lower level is better integrity and better performance in the animal. So we find also here that the inclusion of the functional ingredient increase the status of the intestinal mucosa. Next slide. And after there are here several messages to take to home. For the number 1 is the NeoGiANT product has a moderate effect on fish growth, and the second one is the NeoGiANT product produce a significant effect on intestinal integrity and functionality, and also the product improves the antioxidant response. we can use the last conclusion that we can use the functional ingredient for dietary fortification in aquaculture species. That's it all. Thank you.
Thank you very much, Javier, for that insightful presentation. And now we move on to our next speaker, David Sanchez Peñaranda from SwitchFloc. Please go ahead, David.
Good morning. As usual, my presentation is much simple than Javier. There is no that level.
I'm sorry, Álvaro, please move to SwitchFloc to David. It's not Pedro yet. Yeah, the next one of Javier. Yeah, there. Thank you. Now, David, the floor is yours.
Thank you. No, my idea was only the previous one, please. I don't know. Okay. Now, next. Yeah, it's not like it is in my computer, but it doesn't matter. The point is, my idea was to show you the final results without any data, only the idea, because I didn't want to go too much in detail, only to show you more or less our general results in previous research project, because I comment in the first seminar in SwitchFloc currently is in the requirement period. It means that each institution is carry out the process or the administration process to receive the candidates and also and to perform the selection. Then obviously we don't have any results from the project. And the main purpose was explained also in the first seminar. Then my idea was to show you our general results, we can say, from previous, some of our previous research projects, particularly in BioFlango, sorry, that the objective, thank you very much. The objective of the one was funded by the Spanish Research Council, and the objective was to evaluate, like was our first project related to in relation to the BioFloc, to evaluate the BioFloc contribution to shrimp growth, we can say, or production. To develop protocols to preserve the BioFloc over time. It means because to maturate the BioFloc, it takes some time. So we a good tool that is now is patented, is and should be approved soon, is to preserve the BioFloc, that is a bacterial community, in a short and long period, to use it and to reinoculate it in the future to have a mature BioFloc in a short time. That is quite useful. This was one of our objectives, and also obviously once we have more or less evaluate the BioFloc contribution to the reproduction to conserve the BioFloc, is to design. That is our main topic. Our research line, to design diet composition with low protein content and high fish meal replacement. The next, please. So, firstly, the BioFloc needs to, if you have marine water, clear marine water, you need to maturate the BioFloc. Then, usually to promote the bacterial growth, you need to add common say is fertilize the water. That is the addition of the carbon source. Obviously, this carbon source can be also come from the feeds, but usually to have in a certain time, we add external carbon source. The regular or the most common is to use molasses. It's a subproduct, it's a byproduct, sorry, from the sugar production. That is quite cheap. That we use this carbon source as control group, and we want to compare with different strategies. One strategy is to use an initial carbon bomb that the people common say, that is the yeast that is a source of carbon and nitrogen, so to accelerate the biofloc maduration. But another alternative, this is faster, another alternative is to use a biopolymer that release slowly by bacterial activity the carbon into the system. And these three strategies are more complicated than this, but okay, in general, we combine with different carbon nitrogen ratio. That means that which is the amount of nitrogen? The amount of the nitrogen is the summatory of ammonia, nitrate, and nitrate. So usually when you fertilize at the beginning, is mainly ammonia. So you calculate the N ammonia, so the nitrogen content into the system, and you add in proportion of 10-1, 14-1, 18-1, 22-1, or 26-1, so more aggressive in the fertilization or less aggressive, so to promote this bacterial composition, adding this external carbon source. So when we compare these different strategies, please, molas and no, okay, no, the previous one. Molas and 41. Well, 41 ratio was the best, which provide the best results in terms of growth production. So it means that, and this was more or less like as the literature report. So in this case, nothing different that the people used to do was obtaining our results. When we want, the next step is, we are going to, like BioFloc is provide a natural food. The regular tables that people use for shrimp feeding should be overfeeding of the system. So our idea was to optimize the feeding of the production, trying to reduce the feeding administration, to observe or to check if the BioFloc can compensate this lack of food or this reduction. So what we observed that we didn't obtain a significant difference between 70% or 30% of the reduction, or as the table described. Then we say that a 30% of the reduction of feeding can be achieved under BioFloc system using the tables are referred. Also, we want to, this is a basic, but under BioFloc, the people didn't know very well. So we want to know exactly which was the amount of the total protein can be included in the diet and the BioFloc system, because again, you have a protein, natural protein source into the system, so maybe can compensate a lower content in the diet because they have a natural food. So we determine this the total protein at different levels, because obviously they don't have the same requirements when they are small or they are bigger. So from 0.5 to 5, that is we consider the juvenile growth, more or less. We didn't obtain significant difference with a 38% of the total protein into the diets. The next, please. But when we use a bigger, when we continue this experiment with bigger size, we can reduce the total protein up to 34%. The next. So then we have the best more or less methodology to promote the biofloc maturation. We determine the feeding regime. We determine at different stages of the growth the total protein. Then now we can carry out the fish meal substitution. What obviously, as you know, we have different sources, animal and plant sources, alternative protein source. And our idea was to use only animal, only plant, or a combination of both, trying to reduce the fish meal inclusion that in this control. Okay, more or less 50% is the maximum you can include. So firstly, 50% is our control, and we reduce using this alternative protein source. We reduce a 50%, so it means a 7.5% of fish meal inclusion or a total fish meal substitution. So, and these experiments were carried out in juvenile stage from 0.5 to 5 grams in 1 cubic meter, like you can observe in the picture, and in high stock densities, around 350 animals per cubic meter. Once we finish this first phase, we observe that a diet using only animal protein source or a combination of animal and plant protein, alternative protein source, and a fish meal inclusion of 7.5 were obtained similar result than the control with a 50% of fish meal inclusion. So our idea was to check if these diets can provide these good results also in upper phase, we can say, in a second phase with more from adult commercial size. And we did it in a higher scale. It means previous was in 1 cubic meter, now is in around 3 cubic meters. So that you see in a greenhouse in the picture. So in this, by triplicate, we compare and we obtain next that a combination of animal protein and plant protein source and 7.5 of immune inclusion obtained similar results than the control. Okay, like our idea is to transfer these results to the industry, and the method, the way of working, we can say, in the tanks of even a 3 cubic meters is not totally comparable to the commercial scale. We want to repeat again the experiment from the beginning, 0.5 to commercial size, but in a scale that obviously is not commercial, but we are talking about 14 cubic meters. But the methodology, how you work, is quite similar that you do in a commercial way. So we repeat it, and we confirm that this alternative diet composition obtains similar results to the control. So in 3 occasions, we obtained the same results, that this diet composition was similar to the control diet. Next. Okay, this is for the growth and diet composition, but one of the objectives of the project was to conserve the biofloc in short and long term. So from mature biofloc, next, we decantate it, next, we filtrate to have to more concentrated, next, and we use it as to inoculate a new marine clear water as positive control to compare with a negative control without biofloc. And next, this also was compared that we conserve the biofloc in vacuum conditions during 5 days at 4 degrees in short term. We can consider. Next, we also we frozen the biofloc in this pattern, so it's still and using a chiropotenta minus 80 degrees. And finally, we compare with dry biofloc, conserved during 24 hours with dry 40 degrees, and can be conserved at room temperature during 5 days. And from all these groups, when we compare how were inoculated in clear water and we observe how was the evolution of the maturation of biofloc, it means the peaks of ammonia, nitrate, and nitrate. The best, next please. Similar results were obtained in the vacuum and frozen biofloc to the positive control. Then we can confirm that this methodology of short and long-term conservation can be used to reinoculate a new biofloc in 1 week, more or less. You can, yeah, more or less, depending on the density, but more or less in 1 week you can have a mature biofloc from clear water. That is a very short time. Next. Okay, this the next research project we are going to talk about is the PhytoFloc. That is in this our objective were to set up the environmental conditions for optimum microalgae growth, and to know how affects not only to the growth, but also to the immune system or health status through the environmental challenge. Next. Okay, firstly, as you know, the biofloc, the most tricky part, we can say, is not clear water. So for the macroalgae, it's not the best. So like our first trial was to discover or to find out which was the best initial concentration of biofloc, it means the total suspended solids, so the level of these flocs into the water, to inoculate the microalgae, and both can grow together, we can say, no? And with a normal photoperiod of the 1212 and regular temperature, and we observe next that medium biofloc was the best because zero, obviously, the microalgae growth too much, and if it was too concentrated, the microalgae is delayed in the growth. Next. No, the previous one. This means one less slice. You can go to the next. And the next, no. So, okay, go to, I will explain. I don't know, it's missed. So, then what we do? What we do is we use la Chlorella vulgaris tricornotum with this concentration of total suspended solids, okay? And we submitted at different photoperiods. Total dark, 24 hours of light, 18 hours of light, and 12 and 8 of dark, and 12. And the results that we obtained were the Chlorella vulgaris was much, the behavior of the Chlorella vulgaris was much better in the adaptation to the biofloc environment, so we choose this microalgae, and the photoperiod 1212 was which provide the best result. Then, now the next. Then, when we have the microalgae, the photoperiod, and the initial conditions of the biofloc to perform the experiment, we decide to test how affect the growth, the microalgae addition, compared to another immunostimulant that could be the probiotic addition that is tested, that helps not only the growth, also the immune system. And also we want to know how is the combination of both. So obviously the microalgae need a photoperiod of 12, but the probiotic control were in dark conditions. And this we did it in more or less 1 cubic meter, high, not super intensive one, more or less. Between intensive and super intensive production, around 200 rinse per square meter, and it length around a couple of months. So next. So in terms of growth, which provide the best growth parameters was the probiotic growth. So the microalgae didn't provide this higher growth performance that could be expected or not, because with the probiotic was tested and was already reported in the literature. But when we submitted these experimental groups into environmental challenge, next. Which challenge? Density and anoxia. Why? Which is the reason of that? The sampling. We have a mortality. We need to sample the shrimps every week because the growth is so fast, and we need to adapt the feeding to this continuous growth. So this sampling every week it means a certain percentage of mortality, and we would like obviously to reduce it. So which is the typical environmental challenge that are submitted during the sampling? Obviously density, because in the net are very close, and the anoxia, because obviously some time of anoxia they have. So we want to submit the animals in really quite radical, we can say, conditions that around more than 2,000 animals per cubic meter, and between 2 milligrams liter of oxygen during 6 hours, okay? And we want to observe the mortality, and also we analyze different enzymes in the hepatopancreas, hematocrit in hemolymph, and well, different gene expression in hepatopancreas. But anyway, at the end, our idea is to know in the survival how affects the density, the anoxia, and the combination of both. The combination of both was a little shorter because it was too aggressive. So the next. So when we observe the survival just after the challenge and 24 hours after recovering, we observe in the density next. And next, anoxia, we didn't observe a clear difference. But when we combine both, that was more radical, well, more stronger the challenge. Next. We can observe the microalgae provide a higher survival. What it means? What it means that maybe you don't have that difference in the growth because the probiotic is more heterotrophic. BioFloc, that it means provide a higher protein content into the for the spring, so a higher growth. But when we talk about the immune system, the microalgae seems that provide a better resilience to the environmental challenge. So it's a balance that you can consider. Okay. So sorry for the miss slides, and this is all. Thank you.
Thank you, David, for this insightful presentation. It was really great. So now let's move on with Pedro Luis Castro from Microbiome for Soy. So Pedro, the floor is yours.
Thank you. My name is Pedro. I am going to explain the part connected with aquaculture of this project. Okay, please, next. This project, Microbiome for Soy, next, please, is focused in different aspects about improving soy crops, but also the whole name of the project is Healthier Diets and Sustainable Food and Feed System through employing microbiomes for soy production and further use. Then the project involves different aspects. Next, please. The whole project is led by Angela Sesic from the Austrian Institute of Technology. As I said before, the project involves improve environmental impact of soybean, Also, the effect of this soybean improve in a human gut and also in fish feeds for aquaculture. Always in the frame of from farm to farm to fork or something like that, in the 2030 priorities of the economical union. Next, please. Okay, my institution, the University of Las Palmas de Gran Canaria, reached the project through a special facility, the Hopon facility, that involves to include outmost region of the European Union, such as Canary Island. Next, please. In that way, the project brings together 18 partners from 11 countries. Next, please. And all these partners and work package can be grouped in 4 different actions. Agronomy, focus on identification and improve soybean crops. Food techs, that try to design functional fermented foods and take advantage of the probiotics. Also, of course, management ethics and communication, as Estivaliz do here. And next, please, is an animation. This fourth group. This fourth group focus on nutrition, in human nutrition, and also in the effect of these soy-based feeds effect in aquaculture. Next, please. The work package 4 will be focused on fish feeds in 2 aspects. First of all, our partners in Iceland, Mattis, will be work with salmon salar, with salmon, and our contribution will be made with important economical European sea bass, important species. Next, please. And we will check the effect of this soy from 2 different points of view. First of all, the first part will be developed with commercial soy. Commercial soy in 3 different presentations. Soy meal, concentrated and fermented, but from commercial source, commercial strain. And then a second part that will be developed with the soy improved for our partners and also fermented with bacterial thermostable bacterial strains from our from a library that have our partner in Iceland have. We will ferment it with this strain, bacterial strain. Next, please. Accordingly, we will choose 2 batches, 2 sets. First with commercial diets in 3 presentations at 2 levels, 30% and 45%. And this means 6 diets and a control diet. And we will grow animals until 350 grams with an intermediate sampling at 100 grams. We are doing this sampling, the first sampling next week. Accordingly, we have no proper results right now. The second round will be done with the improved soy from our partners exactly in the same way. The fermentation will be with these thermostable strains that I commented before, but the frame will be exactly the same that with commercial soy. Next, please. We will grow two groups of animal with commercial soy, and then afterwards with the improved fermented soy. And next, please. With this, with the sampling from this next, this is an animation, and with these samples, we will process the commercial soy diets that we are going to start to processing in the next weeks, and afterward the fermented soy dates. Next, we will check the effect of this soy improve and in order to have a control idea with the commercial one from different points of view: digestive, immune system, growth, biochemical, and of course microbiome. Next, please. From the digestive point of view, we will take different sections of the intestine of the SIVAS, and through histochemical techniques, we will, next please, and with image analyze, we will measure the architecture of the folds, and also we will count the different cell types involved in digestive process. Next, please. Connected with immune system, we will count lymphocytic population with this, in this time with immunohistochemistry, and when necessary, we will use in situ in tissues. Okay, next, please. Of course, in order to understand the impact of the diets in the experimental fish, we will take technical measurements, typical to check growth and so on. And next, please. And also, of course, proximal composition to check if there is any change in the experimental animals. And next, please. And also with we will check with microbiome. We will check microbiome in the water and in anterior and posterior intestine. Okay, next, please. We will try to add to this microbiome for soy project the inclusion of a Mediterranean species, SIVAS. We will try to expand the data sets that can be obtained, increase the number of the stakeholders interested, and also our expertise in aquaculture production. Next, please. As I said before, the project is under development right now, but we expect to add evidence of the effect of the soybean, the improved soybean diets, a more detailed understanding of the good health and microbiome modulation, new and robust data of the performance and the tissue response in 2 life stages at 100 and 350 grams commercial size, and the contribution to sustainable aquafish and reduce fish meal dependence. Next, please. Feel free to contact. We have no proper results right now, but feel free to contact, and thank you for your attention.
We appreciate your time, Pedro. And next step that will confirmed by Felipe Aguado Jimenez and Oscar Monroy from CSIC. The floor is yours, guys.
Hello, good morning, everyone. My name is Oscar, and I'll be reintroducing the POLYPUFA project. Next slide, please. So, as I said in the previous webinar, this is a two-branch project. One is led by myself and Juan Carlos Navarro, who couldn't attend today, from Torre de la Sal, an institute located on the east coast of Spain. And then there are two work packages that are led by Felipe Aguado, and he will be presenting the results on those two packages, work packages, later on. So next slide, please. So in the first work package of the POLYPUFA project, at Torre de la Sal, we are aiming to develop mutant strains, knockout strains of this polychaete, Platinum dumirili, and these strains lacking key genes involved in the biosynthetic pathways of launching PUFA. These are essential compounds that are required in aquatic animals. They also provide good quality, good value in terms of nutrition for consumers. And we are trying to develop polychaetes as de novo sources of these compounds for the industry, for aquaculture industry. In this particular case, we are looking into very fundamental mechanisms by developing, as I was saying, these knockout strains on this particular species. I'm afraid I'm not able to show any result at this particular moment because this is work in progress. We've been designing guides that target specifically 7 genes, the saturases and elongases that this species has. And it's a bit more challenging than knocking out genes in fish. In our institute in Torre de la Sal, there are groups that manage or use this technology, CRISPR-Cas9 technology with fish, with zebrafish embryos. However, Platinum dumirili embryos are a little bit smaller and more difficult, more challenging to knock out and manage. So, as I said, this is work in progress, so I'm unable to show you any result on this work package at this particular time. Next slide, please. In work package 2, we were willing to test the hypothesis that freshwater adapted polychaetes have higher capacity to make endogenously omega-3 launching PUFA compared to marine counterparts. This is based on the fact that freshwater species do not have access through the diet to these compounds preformed. As you may know, freshwater environments are significantly poorer compared to marine ecosystems in terms of omega-3 launching PUFA provision. And we were wanting to know whether polychaete, freshwater polychaetes might have developed or evolved as a species with enhanced capacity to make these compounds themselves. We tested that hypothesis with Namalicastis rhodocorder, which is a polychaete that inhabits Nipa palm forest in Malaysia and the surrounding areas. And what we did is we isolated genes encoding desaturases and elongases. We expressed those genes, those enzymes in yeast and tested their functions. And we were able to plot which reactions these enzymes, desaturases and elongases can operate. And this is how the pathways look like in this species at the bottom of this slide. But basically, it resembles a lot like pathways that we have already reported in marine species, with the particularity that in this particular species, freshwater adapted species, Namalicastis rhodocorder, it seems that they have enhanced capacity for elongation of fatty acids, which is a evolutionary advantage when you don't have these compounds preformed in the diet, as I was saying. This is a paper that we published on reporting on this data that you can find online. And this is everything I had to say on the IAT's Torre de la Sal branch of this project. So I give the floor to Felipe Aguado.
Thank you, Oscar. Good morning, everybody. Please, next slide. Okay, now I'm going to show you the result of some of the trial we have developed in this more technical part of the project. The main objective was to develop a diet for Evista diversicolor, a marine polychaete, formulated using agri-food byproducts and find with the final aim to test these worms as a potential ingredient for aquaculture fish. Okay, then we have two work packages. The first one, you can see the title in the slide, and it was divided in several tasks. The first one was to assess the growth of a listed diversicolor when fed mono-ingredient diets using agri-food rest raw material, and in terms of growth performance and fatty acid profiles. Okay, we selected several agri-food rest raw material from the beer industry, like the brewer spent grain, the wine industry using rose and red wine lees, but also grape skin and the grape stem. From cider industry, we use the cider apple skin, and for aquaculture industry, we used BioFloc wastes, those that David showed previously, freeze dried BioFloc, and also RAS sludge. In order to look for a greater protein content, we also try with other potential ingredients that some of them are usually included in the fish feeds, like soybean meal, rapeseed meal, pea meal, meat and bone meal, and pork hemoglobin. In terms of growth, we could see that the brewer spent grain, the BioFloc wastes, and the rose wine lees provide the best specific growth rates. Next slide, please. Then we have to set several criteria for the raw material selection, and also what's the fatty acid content of the worms that have been fed with this raw material. Then we could see that the amount of polyunsaturated fatty acid in the worms that have been fed with beer spent grain was a very good level, and also particularly those worms that have been fed with rose wine lees. You can see in the orange column is the amount of polyunsaturated fatty acid in the raw material, and in the blue column is the amount of polyunsaturated fatty acid in the worm. Then rose wine lees and BioFloc wastes produce facilitate that the worm produce a very high amount of polyunsaturated fatty acid. Then we selected these three raw materials for the next step in the project. Next slide, please. Then we formulated specific diets for this diversicolor using this selected raw material. We formulated 4 diets whose composition is shown in this table, and also the macronutrient content and the main fatty acid and amino acid that they included, using several different percentages of beer spent grain, BioFloc, and rose wine lees, and we use also soy meals in one of these diet, and meat and bone meats in another one of them. Then when we perform the trials in terms of a specific growth rate, we could see that the best results were obtained with were very similar, with the exception of the soup 2 diet that only included 2 raw materials, but the growth performance with the other day was similar, no? Then we have to next slide, please. We have to look for the fatty acid content in order to select what of this diet will be selected. when we can see the sub 1 diet and the sub 2 also, but the sub 2 perform a better growth, but they differentiate in terms of the fatty acid profile respect to the other two diets. And in the table, we can see the fatty acid, the polyunsaturated fatty acid content, and was very interesting in this diet. Then we selected this, which was composed with 20% of beer spring grain, 10% of BlueFeed wastes, and 70% of rose wine lice. Next slide, please. Other task that we have to perform to optimize the culture protocol of this polychaete is to know how is the feeding rate of this worm. It has never been evaluated previously in any other worm. Then we perform an experiment with different weight classes of worms, different densities and different temperature in rest condition, using commercial winning pellets of very, very small size, and with image analysis, we know the amount of pellet that we provide to the worms, and we can count how many they feed every day. Then we using experimental units specifically designed to work with this polychaete. Next slide, please. If you can push the play in this video, we can see how the worm fall out from the hole and is taking the fish feed pellets and swallow. And once they have collected some of them, they go back again to the hole. If we put blue light, we can see very well where are the pellets of the sun, and it's very easy to count them using an image, for example, image G software. Okay, next one, please. Then we assess the using multivariation analysis. We can develop specific feeding rate models and also feeding efficiency. Next one, please. Finally, we can develop feeding charts to feed these worms at different temperature and different densities. Okay, next one. The next step was to get a biomass intensification of this worm fed with the diet that we have previously formulated, and that what this work is now in progress. We have recently, Francisco, you know, we have recently begun with the worm biomass intensification. The aims is to produce a significant biomass to produce a meal from these worms, and to add this meal into ingredients or additive in fish feed pellet to assess the growth performance. This is the near future and the final objective of these two work packages. Okay, I think I have finished. I don't know if there is any other slide. If you put the next slide, we know. Okay, that's all. Thank you.
Okay, thank you both for your presentations. So now let's move on with ActFast. So Luca, all yours.
Yeah, thank you. Good morning, everyone. My name is Luca Parma from the University of Bologna, and I will briefly introduce the aim and the methodology that ActFast will foresee in feed. ActFast is an innovation action project under the Horizon Europe program, with the aim to find solution for climate adaptation and mitigation for aquaculture in several in different European environments. The project will have a specific regional focus, an area on the Mediterranean, deltas in Po, Ebro, and Nile in Central and Eastern Europe and in Northeast Atlantic. The project is a clear industry-driven approach with important collaboration among industry and academic, with the final aim to enhance productivity and circularity of the aquaculture sector. Next, please. Is coordinated by the University of Bologna and is involved 28 partners from 10 different countries. The project has just started in last June, and it will last for 4 years. Thank you. Next. Within the project, there will be several 30 key exploitable results that will be developed to high TRL, and 5 of them will be related on feed in different species, in particular on European sea bass, on carps, and on Atlantic salmon, with different purposes. And today I will introduce some methodology of some of them. Thank you. Next. A first innovation is climate correct aqua feed for European sea bass using low carbon and circular ingredients. In the context of the rising temperature of the Mediterranean, the animals are facing differences in metabolism, so also the growth curves of the animal are changing. The maintenance energy costs are increasing. So there will be the objective of optimizing, rethinking the protein energy balance under chronic high temperature, with the aim to reduce nitrogen losses and also optimizing nutrient efficiency, nutrient allocation, so to have a more stable growth during longer warmer period in the Mediterranean, and also increase feed efficiency, so also giving a mitigation effect of the feed. Next. This innovation will be led by the University of Bologna in collaboration with Scretting and with Cromaris. It will see a first lab experiment that will be then tested, demonstrated in field. We will set up several diets with different protein and lipid content, and tested with different temperature environment, high temperature condition for chronic exposure. All the diet will be formulated using an industrial approach with zero waste approach, including the ingredient that aim to reducing the marine ingredients, including byproducts from fish aquaculture. And then it will be tested and see for several measurements, including feed efficiency, metabolic parameter, appetite, and the best solution would be finally demonstrated in field. Next, please. A consequence in the diet will be also optimized. In this case, the objective is to enhance, to test a functional feed in order to combine, to reduce the combined effect of heat waves and pathogen. In this case, functional feed will be added to the previous formulation and tested in under exposure of heat wave in combination with different biotic challenge with bacterial that are, for example, expected to increase, such as from Vibrios. And several measurements will be also tested, including mucosal health parameter and the microbiome, for example. This innovation will be led by IRTA and also together with Scratting. Next one. Climate change is not only high temperature in the summer, but it means also high temperature in winter. These affect carp farming because we have a longer cold period that's increased the fish to eat in the winter. Winter heat wave are also affecting carp productivity. So all of these at the end affect also the survival of the juveniles. So in this case, the objective is to develop a climate-adapted winter for carp, identify the thermal minimum for feed uptake, which is also the optimal digestible energy protein requirement for carp at a low temperature, and including also immunostimulant and functional feed to cope with cold period during winter. So at the end, all these will be combined in developing winter feeding technology for industrial application. Next one. This task, this innovation will be led by the Hungarian University of Agriculture and Life Sciences in cooperation with Feed Industry Garant and with BHG, which is the biggest pond farm, one of the biggest pond farm in Europe. Again, the trial will follow a lab experimental trial with different diet, including different digestible protein, digestible energy ratio, following environmental challenge test that is during the winter. This innovation will be also further tested at industrial scale after the first preliminary laboratory experiment. Next one. So I ended my presentation. These were some of the innovation that will be carried out during this process that has just started. So please follow us, follow in www.actfastproject.eu or on LinkedIn. So we'll stay tuned that the project will surely we are open to invite you in several workshops or events that we are going to have. Thank you very much.
We are grateful for your time and work, Luca. Thank you. And now to close on a high note, please welcome Sandrine Esquiva from auequa.org.
Okay, thank you very much to give me the opportunity to talk about the auequa.org European project. So I'm Sandrine Esquiva. I'm a researcher at the National Institute for Agriculture, Food and Environment in France. So next slide, please. So in the auequa.org project, which is dedicated to selective breeding and organic aquaculture, there is a special work package dedicated to selective breeding for feed efficiency using cost-effective and health-improving feeds. So with Luca Parma from University of Bologna, as well as Joaquim Gutierrez from University of Barcelona in Spain, we are involved in a particular task dedicated to the assessment of cost-effective organic diet to improve organic aquaculture. And I will talk about, I don't want to present you results, but I will present you our scientific strategy we are developing to develop new organic diets. Next slide, please. Okay, organic diets as a strict regulation that involve heavy use of fish meal and fish oil in current organic feeds. Why are we using a lot of fish meal and fish oil in organic diets? It's because there is a lot of constraints and limitation for organic fish feeding. First of all, we are using a high level of fish meal because there is only a limited number of plant protein sources available for organic farming. Secondly, there are many ingredients that are not allowed in organic agriculture, such as protein from terrestrial animals, insects also. And we cannot use synthetic ingredients such as amino acid and especially methionine and lysine, so we cannot balance the diet to fulfill the nutritional requirements of the animals. We cannot use pigments if they are not natural, and we cannot use antioxidants. GMO and products derived from GNO are also not allowed. We can use microalgae, spirulina, or other microorganisms also only if they are produced in accordance with organic regulations. Next slide, please. Okay. So the objective of this part of the project euaqua.org is to maximize fish meal and fish oil replacement to design cost-effective and sustainable organic diets to provide multi-performant fish. This will be done on two main species, the gilded sea-bream, using two selected families that has been selected on their growth potential, and also on the rainbow trout. And finally, in rainbow trout, the novel diet, organic diet, will also be tested on a genetic line that has been selected for higher growth on plant-based diets. Next slide, please. Okay, when we talk about performance, the originality of this project is that we are not going to limit the evaluation, the assessment of the diet at the level of the production, but we will also include performance at the level of the quality of the product, animal welfare, fish robustness, and also the environmental impact of the diet on the production, because we know that the environmental impact of the fish production is mainly supported by the environmental impact of the feed. Next slide, please. Okay, so there are ongoing experiments on rainbow trout and on gilded sea-bream. On rainbow trout, our first step was to evaluate the performance of a current conventional diet compared to a current organic diet. That's the reason why we are we have currently a growth trial in which we compared three diets: a conventional diet with 22% of fish meal and 4.8% of fish oil, and we compared it to different plant ingredients, and we compare it to a bio-organic diet with 46% of fish meal, almost double of the conventional diet, 8.5% of fish oil, and for the organic plant ingredient, we have only organic soybean oil, organic soybean meal, organic faba bean, and also organic wheat. And in this organic diet, we can't use lysine and methionine to balance the diets. And then we have formulated another non-organic diet, but with the same formulation of the organic diet, but the ingredients were coming from conventional agriculture. So all the diets were isoproteic and isolipidic. And we are testing this diet also in a digestibility trial in order to see if there is an impact on the digestibility of the feed. Okay, next slide, please. There is a similar experiment that is developed in CBRIM with a comparison between a commercial conventional diet and a commercial organic diet. You can see that there is a large difference in terms of fish meal level, 23% for the conventional one and 40.9% for the organic one, and also a few plant protein sources for the organic diets. And in this experiment, Luca, my colleagues from the University of Bologna, is also testing a new organic diet in which we try to reduce the utilization of fish meal from 40.1% to 23% by using yeast, which is a novel organic ingredient that is developed by L'Allemand and that is certified for organic utilization. And also, in this diet, we included poultry meal certified for organic production that help us to balance the diet in terms of amino acids, because in these organic diets, I repeat that we cannot use amino acids. Next slide, please. Okay, so the general protocol we are following is that we are testing the diets in triplicates. For the rainbow trout, the duration of the trial is 12 weeks with a measurement of the biomass of the tank and the feed distributed every 3 weeks, which give us the possibility to determine the zootechnical parameters, both the specific growth rate, the feed intake, as well as the feed conversion ratio, so the feed efficiency. And at the end, we will collect many samples, whole fish, but also many samples, muscle, blood, head, kidney for robustness, for example, and also samples from gut to measure different parameters with biochemistry and molecular biology, and also quality parameters. Okay, that's all for me, because we not the results, and I hope we will be able to give you the results of this experiment in the next in a future webinar. So thank you very much for your attention.
Okay, thank you so much. So, well, right now we are reaching to the end of this webinar. So thank you to all our speakers for their valuable contributions. So the question time is open. So if you have any question, please write it down in the chat of the meeting, or up there you have a Q&A section on the little bar on the meeting. In any case, you would like to ask anything to our speakers. So let's wait a couple of minutes if you would like to ask anything. So if not, we can just close the session, but just wait, okay? See anyone else has anything to say or ask?
Estíbaliz, good morning.
Hi.
Only one question, but it's a general question.
Okay.
It would be possible to get some kind of certificate of participation of the projects in the cluster?
Yeah, no problem. Yeah, we can make that.
Okay,
yes.
Thank you.
Okay. Well, we'll see. Everything was really clear. We don't have any questions. Oh, okay.
I wrote in the chat.
Okay. Yeah. Thank you, Felipe. So let me answer. Yes.
if you let me, please, another comment. I show very interesting all the contribution, but particularly from our particular interest, I like a lot the use of grapes and other ingredient in the fish feeds, because it's very close to our approach. The use of some non-common ingredient to feed the feed. Then I think that if in any moment some of you want to perform some experience in the context of a project, including the use of polychaetes, we have a unit of polychaete production in our facilities, and we can produce polychaetes on demand, and this polychaete can fit what you want in order to get a final polychaete composition that could be tested in any kind of feed. Then I send this message. If anybody at any time want to try something with us, we will be very pleased to do that.
Yeah, thank you, Felipe, for that. So, well, guys, if we don't have any questions or anything else, I think we can finish this webinar. Thank you, all the assistants, to be here. We were going to upload the video in any case you just missed the webinar in our social media, so stay tuned for that. And again, thank you all to the speakers and attendants to be here. So that will be all.
Thank you. Bye.
Bye-bye, guys.
Thank you.